Good morning. Welcome to Krishna's classroom. We continue with our discussion on derivatives. And it's essentially our objective is to connect differentiation and integration and also look at the fundamental theorem of calculus or fundamental theorems of calculus in the context of Lebesgue integration. So we introduce now the concept of what are called upper and lower derivatives of a function. Now the function may not be differentiable, but both the upper and lower derivatives exist. Now this is the important. Okay, so we will define such a thing and later look at a situation when this function is differentiable at a point in terms of the behavior of upper and lower derivatives. So we start with a real valued function. So let f be a real valued function from some interval ab. This need not be bounded. Okay, but since we are working only on a local phenomenon, doesn't matter. Okay, real value function, and let x be needless to say that this. Now, incidentally, we need not even assume that the domain of the function is an interval. It is some subset of the real. In fact, we take the domain of the function a subset of R and take x to be an interior point of domain. So for all interior points of the domain, we are going to define what is called the upper and lower derivatives. So let us define this. The upper and lower derivatives. X are defined as we first define upper derivative. This is denoted by d bar f, not below but above. So d bar f is defined as what? At the point x is defined as limit h tending to 0, supremum of 0 less than h, less than mod p So you can take the supremum of this. The supremum is taken over t that lies between 0 and h. Now, this is how you define it. So you have the point x. Now, you take the interval plus h. Okay. Now, what is this? Taking the point x and then you are taking a point x plus t. Now, t may be positive or negative. In either case, you see that f of x plus t minus f of x. So, suppose the function has a graph something like this, then this is going to be, this is going to be x plus t. So, this is of course x plus h. This is the interval. So, you have f of x plus t. F of x plus t is this height minus f of x, this height divided by t. Okay. So, that is the slope of the chord. As you know, your usual definition of this or usual understanding of this ratio. And similarly, on the other side also, if t is negative, then you are going to have x minus t rather. So, I am taking t positive in the figure. So, then you have what you call, in that case, t lies between 0 and h. Okay. So, you have got f of x minus t minus f of x divided by t. Rather minus t. Okay. So, you have this definition. Now, these are all talking about the slope of the chord connecting x plus t and f of x plus connecting the point f of x plus t and f of x. I mean, strictly speaking, x plus t connecting the point x plus t f of x plus t. This is the chord that you are talking about to x. So, you connect these 2 points. That's the chord that you are talking about, and then finding the slope of that. And you can take both t positive and t negative. Okay, so that's very clear what exactly the geometry is. It is better to understand this geometry before we proceed further. Now, you see that for each h, these numbers have a supremum. as t moves over 0 to h, or mod t moves over 0 to h, there is going to be a supremum. The supremum exists. Okay. In the supremum exists provided you are working in the extended real line. Okay. So we work in the extended real line to calculate this. Otherwise, for bounded functions, everything is nice. Okay. So we work in the, so we take f to be from the domain to what you have as this is okay. I mean, this is okay. This is what you have. But then this ratio, you are seeking the supremum in the extended real line. That means also it may take plus infinity and minus infinity. That is possible. Okay. So calculate that for a fixed h. Okay. So you have on the interval x minus h to x plus h, where you calculate this ratio and then look at the supremum. We will work out an example then. And then you see that as h goes to infinity, what happens to this supremum? This supremum is going to be a decreasing function. This supremum is going to be a decreasing function. And therefore, the limit exists. The limit may be minus infinity. Don't know. Okay. So we are seeking the limit in the extended real line. Okay. So that number, whatever you get, so what I wanted to say is that the limit exists. Okay. Right. So that is what you call d upper bar fx. Okay. Let us take an example. Then it will, what's that? Let's start with the bounded function. First example, take a bounded function, and then after that we will define lower derivative. That we will soon. But before that, let us understand this. Take mod x. Now you know that f0 is 0. You know that f is not a continuous function and not differentiable at at 0. Everywhere else it's fine. In the, if x is positive, then the derivative, f derivative of x is going to be 1. If x is negative, because you know that the graph of the function is this. This is fx equal to mod x. Now you see that the left derivative and the right derivative you have. In this case, it's a nice function, except for the non-differentiability at the point x equal to 0. Now let us calculate d bar f. Now d bar f at 0 we are calculating. This is equal to limit of You can also replace this by limb soup. So you can call this the limb soup. Okay, so you are taking the infimum of the supremum. 0 less than mod x. Some people prefer to write it that way. Less than or equal to h of what is f of x plus t? F of x plus t is mod t depending on what t is. Okay, so you have two things. One, f of x plus t is ft. So it's going to be minus 0 divided by, okay, let's calculate this because f0 is 0. So what happens to this? This is, see, there are two values. Now we take this as on two portions and then take the supremum. So you have two things. One, you see, on t positive, okay, so h is positive, so we take this into two portions. So limit h tending to 0 of, you have two portions when t is positive and when t is negative. When t is positive, it is going to be t divided by minus t. This corresponds to the positive part, this corresponds to negative part. What is all this? This is equal to minus 1 plus 1. So supremum of this is going to be this one. Okay. We write here supremum. What is that? That's equal to 1. For any h, it is independent of h. Therefore, you see that this is equal to so we shall compute, and this is equal. So limit h tending to okay, right? So that's equal to 1. Whether you start from this side or that side is immaterial. The supremum is always equal to 1. Okay, right. Now, so d bar plus 1. Now let us take another example. Now we will come back to the same problem and compute what is called the lower derivative. Okay. So let us define lower derivative. The lower derivative of at x is defined by instead of supremum you take the infimum. So limit h tending to 0 is the same. You take the infimum of 0 This is the definition of the lower derivative. And let us calculate in this case what this is going to be. In the same example, we get limit h tending to 0 of infimum of 0 less than or equal to mod t less than or equal to h. What is that you get here? Again ft by t, same thing. What is this? This is going to be, there are two numbers there. You have, it is the infimum of two numbers, namely -1 and 1. Again the same number. Okay. And what is that? That's going to be equal to minus. So which turns out to be in this case the left. Okay. The other one turns out to be the right derivative in this case of this function. But we may not have these things true in all circumstances. Okay. So you see that in this particular example, mark this function, we get d sub bar f at 0. This is going to be that's something that we understand. So we have defined both the upper derivative and the lower derivative. Now we are allowing the limit value to take the extended real value. Okay. So that's the definition. Now let us look at a more sophisticated or complicated example, which is going to be somewhat interesting. Let us take the function, second example. Let us take ft to be equal to the characteristic function of the rationals. Okay. Okay. This is the function which you know is equal to 1 whenever t belongs to q and 0 q complement. That means at the irrationals it takes the value 0 and at the rationals it takes the value 1. That's very interesting. Now we will compute the derivative at an arbitrary. Okay. So let we split this into two parts. It's complicated. We split this into two parts. One, we take x belonging to q. Then you see that fx equal to. Therefore, you look at this ratio. Therefore, what is this? If you look at this ratio, then you see that this is equal to zero whenever t is, and what happens when it is, and this is equal to, if t belongs to q complement, then it is going to be then x plus t in that case is going to be irrational. And what will you get? The value of the function is 0. 0 minus x is rational, therefore this will be minus 1 by. Therefore, now we are going to consider the following set. Take h positive. Now, in this case, what is going to happen when t goes to 0? When t goes to 0, you see that f of x plus t goes to fx. Okay, so that's the situation that we are considering. And if you take an interval x minus h to x plus h, what is this ratio likely to be? Okay, it will be, we are taking the supremum of this. I mean, these are the values that you have, 0 minus 1 by t, and then we are taking the supremum over mod t h. What will be that? See, it's going to be, the absolute value of this is going to be 1 by mod h, right? So it's going to be what? So it is going to be 1 by mod h or 1 by mod t with the appropriate sign as minus. So what will you get as the limit? The limit in this case is going to be minus infinity. This goes to minus infinity, or what you call the supremum. So let us take the supremum. Okay, we have to do another analysis also. What happens if, okay, we are taking the case where x belonging to q. Okay. So we have considered the case where, yeah, both these situations where t is a rational number. In that case, you will get 0. We consider the case t belonging to q complex. So it is going to be minus 1 by t, whatever that may mean. Okay, right? And therefore, you will see that you have from one side, it is going to be negative, and from the other side, it is going to be positive. Okay, so what happens when you take the supremum? Supremum is going to be equal to this is what. Okay, so when t is positive, it is going to be, this is going to be and t negative, it is going to be let us write it this. Okay, so that happens when t is taken as the t is, okay, we have taken x, q and t. Yeah, we have considered both the cases. Yes, when t belongs to q and t belongs to c. Therefore, what is the supremum? So limit, or what you call t bar going to be a simple. So we have considered this scenario. What happens when, okay, what we take next is the same thing with x belonging to q. Take the case x belonging to q complex. That means x is irrational. Now we take the interval now in this interval we try to calculate. The h is taken as positive. Okay. Now what is that you are again looking at this one, f of now we have different cases that you have to consider. Okay. So this is irrational. Therefore, this is equal to, by definition, f of x is 0. So this is going to be f of x plus t divided by t, since f of x equal to 0. So what are the values that this can take? Okay. So the values that this can take are the following. One, of course, t is suppose t belongs to q. Then you are going to have f of this is going to be f of x plus t is what? When t is q, you are going to have x you have already chosen as irrational. Therefore, this is going to be irrational. Therefore, you see that it's going to be 0. When t belongs to q complement, now there are two situations that you have to consider, but x plus t belongs to q. That is possible. Okay. In that case, what is going to be the same case? We will have f of x plus t is this is going to be 1. This is going to be 1 by t. Okay. T line t may be positive or t may be negative. Okay. Now let us take the case where t belongs to q complement, but x plus t q complement. X plus t is irrational. In that case, f of x plus t minus is going to be again 0, because f of x is 0, f of x plus t is also 0, therefore this is 0. Okay. So it is going to be the 1 by t. Okay. Now we are going to take the supremum of this, right? Therefore, let us see. Therefore, what is it? Okay. So for any interval minus h to plus h, you can find t which is rational, which is irrational, and which is even irrational such that x plus t is rational and x plus t is irrational. All these scenarios would occur. Therefore, you have to look at the supremum of all this. Okay. So you have supremum of t h. This is going to be that's a supremum, because this may be negative, this may take negative value as well as positive value depending on what t is. Okay, so this is going to be 1 by h, right? And limit This turns out to be equal to what? Plus infinity. Therefore, in all these circumstances, what you are going to get as this. So, d bar f at x equal to plus. Okay. So, you see that the function is not differentiable. Neither the left derivative nor the right derivative exists in this case at any point. So, remark nor exists for this function at any point, whereas the upper derivative and the lower derivative exists at any. This is the interesting. So we are talking about something that exists at every point. Whereas you know that the left derivative and right derivative, the conventional ones that we have been used to, does not exist at all. What is going to be the lower derivative? The lower derivative is going to be the infimum of this. Okay, what is going to be the infimum of this? The infimum of this, see, it's going to be 0 and 1 by mod t. Okay. One by mod t and minus 1 by mod. So what happens? This is going to be the d bar x is going to be, in fact, this is what you get. This becomes so it is differentiable at every, it's not differentiable function clearly because it is discontinuities at every point, but the upper and lower derivatives do exist at every point. So that's the point. That's the point. Whereas in the previous example, you had the upper derivative and lower derivative existing, and the upper derivative in fact coincided with the right derivative, and the lower derivative coincided with the left derivative, and they were not equal. Now this was the problem, right? Now one should also work out the following. The third example, that's somewhat fascinating. Third example that you have realized. This is actually oh, now one would immediately see that f is continuous. Everywhere. And a moment's inspection. And what is the nature of this function? This function is this. It oscillates between mod x, between minus x and plus x, and so also here the oscillation becomes more and more rapid as, but then it's all squeezed by the two lines x equal to 0. So this is the function. It is squeezed between minus 1 and plus 1, and you see that the function goes to 0 as x tends to 0. So that is clear. So there is no problem with that. Okay. Therefore, the function question is because the function is differentiable everywhere except possibly at 0. That we don't know. We'll examine that. B bar f0 and what is the lower derivative and the upper derivative, or the upper derivative and the lower derivative, as I have done here at the point 0. Okay. So let us look at this. So we have to examine this ratio. This is what you have to examine. Okay. And what is going to be ft? Ft is going to be t by t. So whether t is positive or t negative, now this is going to happen, and you see that this sine 1 by t, as t goes to 0, you will see that 1 by t rapidly goes through the multiples of or as t goes through the rapidly through this one, 1 by 2n pi. So that as n tends to infinity, this goes to 0. You will see that sine 1 by t will rapidly go through 0 and probably take pi by 2. Okay. Right? So it will be running between, going rapidly between plus 1 and minus 1, therefore multiplied by t. So there is something that moderates it down to 0 or pulls it down to 0 as n tends to infinity. But what happens is the denominator, therefore you see that this goes to 0, therefore, sorry, yeah. Okay, this is what you get, right? Therefore, this is the oscillation of sine 1 by t. Sine 1 by t would oscillate between -1 and +1. Therefore, you get the, depending on whether you take some certain sequence of points, it will be +1 and it's going to be -1, and you'll see that the supremum of that, if you take, this is going to be, so this is what you get, d bar f at 0. Okay, and d bar this is going to be -1, because it's going to rapidly go through the values -1 and +1. So you are taking the supremum of that to taking the infimum of that. So these are the upper integral and lower integral, both exist. This is what it is. Okay, so in this case, the upper integral and lower upper derivative and the lower derivative exist at the point 0, and it is given by this. It will be nice to examine these kind of examples. Now, in all cases, the upper and lower derivatives will exist. Now, this is the point that I want to highlight. So, I hope you got a idea of what these upper and lower derivatives are, and therefore you can possibly examine this particular example. X squared so this is a very interesting part. It's a very interesting part. Right? You see that the graph of the function lies is squeezed between, this is y equal to x squared. This is y equal to minus x squared. So it's going to be something that is again oscillating between these. You see that is much more strongly squeezed at the point 0 by these two curves. Have some. Therefore, the function is a continuous function. Now you can easily see that does the derivative exist? That's also easy. Take this one. See that f0 is, I didn't write it. X dot. Okay. Right? Now you know that the function has its derivative. What is its derivative? And this, goes to 0. Therefore, the derivative is 0. At this point, the derivative exists everywhere. The function is and equal to 0 in at other points there is no more. The sine 1 by x is anyway a bounded function. Okay. what happens? Um, what happens to so compute you'll see that both of them are equal and equal to C. Okay, so you can see that both these are equal and equal. So you might ask, in all cases we have seen allowing the upper derivative and the lower derivative to take values in the extended real line, it exists everywhere. So R star, the extended real line, what you have the function may not be differentiable. That's going to be a different story. Okay. So what we want to ask is this: when is it differentiable? And what one can show is that f is differentiable so one can show the following, that we have d bar fx greater than or equal to that is clear. That's not difficult to see. It comes from the infimum and supremum definitions. Now further, we also observe the following. Suppose is equal to and is finite, then f is differentiable. So the criteria for differentiability of the function is that both the upper derivative and the lower derivative should exist, and they are finite and they are equal. Okay, then you see that the function is differentiable, and the cases that we have examined are, in the case of the first example, you have seen that it's not differentiable at the point 0. Then the second example, Also, we have seen that it is not differentiable at any point, although the upper derivative and the lower derivative exist. In the third example, everywhere else things are fine except at the point 0, where the function is not differentiable. Okay, there you can see this going on. You can see that the upper and lower derivatives do exist in that case. I mean, there is no problem. But the what you call, they are not equal. So that's the case that we have for the third example. Okay, in the fourth example, you can see that it exists everywhere. Derivative exists everywhere. But what is fascinating about this fourth example is that the derivative, the function is differentiable at every point, but the derivative is not continuous at x equal to 0. Okay, so all these oscillating type of examples are fascinating, and this is something that we have the advantage that through this concept of derivatives we could also accommodate what are called the oscillating functions. Now what we examine here is the case, we'll take up the case of the mean value theorem and possible generalization. Yeah. And differentiable on its interior, that is AB, with f derivative at x is greater than or equal to alpha for some alpha on, then what do you have? See, we have this immediately. What is the result? Can write down. Can write down. See, our result says that the following. If derivative at x naught into minus a, where x naught is some point in the interval, and we do not know at what point. So what you have is that there exists, okay, such that it doesn't say what exactly, I mean, the theorem does not say what point it is. Okay, right. Now this is the mean value theorem. And suppose we have this additional restriction that f dash x is greater than or equal to alpha. Then what we get is this. is greater than or equal to alpha times this is the condition. This is the form in which you would like to look at this. Now let us reformulate it in terms of the measure. Okay. So you see that B minus A measure of, that is the Lebesgue measure of the interval. Okay, so I can just simply write, say, let me denote then measure of this interval A. This is what I am looking at. Therefore, I can rewrite this in the form measure. So what do I get? I get this. So from this I get, I am taking a smooth function. So measure of AB is less than or equal to 1 upon alpha into thereby giving an estimate of the measure of. Okay. Now we will prove a sophisticated version of this, where even the set AB, even the set that we consider, the subset that we consider of R may not be, we are not going to consider intervals, may not be measurable. So so measure will be replaced by, but you know that outer measure exists in all cases. Therefore, we will be proving a result of this kind, M star of the set that we are going to, is going to be 1 by alpha. Okay, so we are going to work on this result, because the subset that we consider will be not merely the interval AB, but the place where f derivative has this property that f derivative x is greater than or equal to alpha on a. Right? So I think we'll stop here, and next time we'll go for the generalization of this result. Thank you very much.